So you've probably heard people talk about quantum computers, right? And the usual take is that they're just super fast versions of the computer you're using right now. But here's the thing. That's not just wrong. It's completely missing the point. The whole mind-bending point. To really get it, we've got to throw out our old ideas of what a computer even is.
And this quote right here, it just perfectly nails it. A quantum computer is not just a more powerful version of our current computers, just like a light bulb is not a more powerful candle. I mean, think about it. You can make the best, most efficient candle in the world, but it's never, ever going to become a light bulb. They're based on totally different principles. That's the exact same leap we're talking about with quantum computers.
Okay, so let me give you the best analogy I've ever heard for this. Imagine your regular classical computer is a really fast car. You can tune it up, make it faster, more fuel efficient, but at the end of the day, it's stuck on the road system, right? A quantum computer, well, it isn't a faster car. It's a boat. The point isn't to go faster on the same roads. It's to travel across vast oceans of problems that a car could never, ever get to.
So to really feel that difference between the car and the boat, I want you to play a little game with me. Well, you'll be playing against a computer. The rules seem super simple, at first anyway.
All right, here's how it works. We start with a coin showing heads. The computer gets the first move. It can either flip the coin or do nothing. You don't get to see what it did. Then it's your turn. You can flip it or not. Again, your move is secret. And finally, the computer gets one last secret move. If the coin is heads at the end of all that, the computer wins. If it's tails, you win. Now, with a normal computer, this is just a game of chance, right? It's got to be 50-50. But what do you think happens when the computer you're playing against is a quantum one?
Well, the results are kind of shocking. In a test with 372 games, the quantum computer won 97% of them. 97%. And get this, the only reason it wasn't 100% is because of tiny little errors in the machine. So what does that tell you? It's not just lucky, it's playing a completely different game than we are. So how? How is that even possible? It feels like magic or like it's cheating, but it's not. It's just quantum physics in action. It's using the super weird, totally counterintuitive rules of the world at a subatomic level. And to get our heads around it, we've got to throw out the rule book we're used to.
All right, so let's crack open this new quantum rulebook and see what's going on. There are a couple of key ideas here that honestly sound impossible, but they're the foundation for this whole thing.
Okay, so everything starts with the most basic piece of information. In your computer, that's a bit. A bit is like a light switch. It's either off, that's a 0, or it's on, that's a 1. Simple enough. But a quantum bit, or what we call a qubit, well, that's where things get weird. A qubit can be a 0 and a 1 at the exact same time. This crazy idea is called superposition. The best way to think about it is like a spinning coin. While it's in the air, spinning, is it heads or tails? It's kind of both, right? It's this blur of possibilities. That's a qubit. It exists in this fluid mix of 0 and 1, holding on to all that potential information until the very second we look at it or measure it.
And that right there, that's the solution to our coin game mystery. See, the quantum computer wasn't guessing. It didn't have to. On its first move, it put the coin into that superposition state, a state of being both heads and tails. So no matter what you did on your turn, flip or don't flip, the coin just stayed in that fuzzy in-between state. Then, for its very last move, all the computer had to do was force the coin to choose a side, and it chose heads every single time.
But superposition is just the first piece of the puzzle. The real superpower, the thing that scales this up to incredible levels, is something called entanglement. You might have heard of it. Einstein famously called it spooky action at a distance. Basically, you can link two qubits together so their fates are intertwined. They become one single system. And the weird part is, if you measure one, you instantly know the state of the other one, even if it's millions of miles away.
And here's where your brain might start to melt a little. The power of this stuff grows exponentially. The scale is just nuts. Get this. If you wanted to describe the state of just 500 entangled quantum qubits using a classical computer, you would need more bits than there are atoms in the entire known universe. Let that sink in. A regular computer can't even write down the problem, let alone have a hope of solving it. So, okay, we have superposition and entanglement, which together open up this just unimaginable computing space. So what do we do with it? What are the problems? What are those new oceans that our quantum boat can finally help us explore?
Well, the potential is absolutely game-changing. For one, nature itself operates on quantum rules, so we could finally simulate molecules perfectly. Think about designing new medicines for diseases like Alzheimer's, or creating revolutionary new materials. We could also tackle insane optimization problems, like finding the absolute most efficient shipping routes for global logistics. And then there's security. Quantum computers could create perfectly unbreakable encryption. But they could also have the power to break most of the encryption that protects our entire internet today. It's a double-edged sword.
Okay, so before we all start planning for our quantum-powered future, we need to pump the brakes a little bit. It's so important to understand that actually building these things is one of the biggest engineering challenges humanity has ever faced. There are some huge, huge problems we still have to solve.
And the number one enemy, the biggest challenge by far, is something called decoherence. You see, qubits are incredibly fragile, unbelievably sensitive. The tiniest vibration, a little bit of heat, even a stray magnetic field can knock them out of that special quantum state. It's like the universe is constantly peeking at them, and as soon as it does, poof, the whole calculation is ruined. And that fragility forces us to go to some pretty extreme lengths. To protect these qubits from decoherence, they have to be locked away inside these huge, elaborate refrigerators, totally shielded from the outside world. And they have to be kept at temperatures that are actually colder than deep space. We're talking just a tiny fraction of a degree above absolute zero. It's an incredible feat of engineering.
So what's the big takeaway here? A quantum computer is probably never going to replace the car, the laptop or phone you use every day. But honestly, that was never the goal. The real question, the exciting question, is this. As we get better at building these quantum boats, making them bigger and more stable, what new worlds are out there for us to discover? What solutions to problems that we think are impossible today will we finally be able to find across that ocean?